After our review of basic statistics, we're going to jump right into an example question from the social sciences. Let's examine the question, do hospitals make you healthier?
People don't want to hear about home birth. They're like, oh, you had your baby at home. Yeah, we were going to do that, but we wanted our baby to live. People always assume there was some laziness involved. You didn't want to go to the hospital? It was far. I didn't feel like putting on pants. We had our baby at home, not in a field. At home? Well, why wouldn't you have it in that germ-infested building where sick people congregate? Didn't your wife want to give birth in a gown someone died in yesterday?
Okay, so how would we go about investigating the answer to this question? The simplest approach would be to ask a bunch of people, both in and out of hospitals, to rate their health on a scale of 1 to 5, 5 being the best. We could then compare the mean health status of people in hospitals to the mean health status of people not in hospitals using the t-test we discussed last week. Well, the National Health Interview Survey in 2005 did just that. Using their data, we can see that the average person in the hospital rated their health at 3.21 out of 5, and the average person not in the hospital rated their health at 3.93 out of 5. Using the standard errors, we can see that the difference between the two groups is statistically significant. Our data shows us that people in the hospital actually rate their health lower than those not in hospitals. So it looks like hospitals actually make people sicker. Maybe being cooped up with other sick people cancels out the effect of all the treatment people are getting there. Or maybe this proves that modern medicine is a sham being peddled by big pharma.
I'll call my congressman.
You just don't get it, do you? Who do you think runs Congress? Big Pharma. It's the big pharmaceutical companies, Glenn, that make all the big decisions. Big Pharma paves your roads. Big Pharma delivers your mail. Who do you think teaches your kids how to read? Teachers? Try again. Big Pharma. Big Pharma took us to war in Vietnam, synthesized crack, and killed Kennedy. Big Pharma came from outer space, invented Ben Franklin, started a little company called the Internet, and polluted the ocean with high fructose corn syrup. We're everywhere, Glenn. Even this is Big Pharma.
Or maybe I'm making a huge mistake. I've already started drawing causal conclusions from our data when it's not appropriate. To better understand the mistake I'm making here, we're going to need a bit more terminology. You're likely already familiar with the terms independent and dependent variables. Another word for the dependent variable is outcome, which we can represent with the variable y. Y with the subscript I is the outcome for unit I. For example, y sub 3 here is the health of person 3 in our sample. For independent variables, the simplest variety is binary, meaning it can only take 2 values. Our hospital example has a binary independent variable. Someone is either in the hospital or they're not. Another word for an independent variable like this is a treatment. People in the hospital are called treated, and people not in the hospital are called control. We can represent our treatment with the variable d, which is equal to 1 if an individual is in the hospital, and 0 if an individual is not in the hospital. The subscripts also apply here too, so d6 equals 1 means that individual 6 is hospitalized in our sample. Okay, so we have our treatment variable and our outcome variable. But to really understand what's going on here, we need to think about 2 more variables called potential outcomes. Let's call them h and n. For each individual, variable h represents what that person's health would be if they were in the hospital, and variable n represents what a person's health would be if they weren't in the hospital. So h5 is what person's health would be if he was hospitalized, and n sub 5 is what person 5's health would be if he weren't hospitalized. The thing about these potential outcomes, obviously, is that we can only observe one of the 2 potential outcomes per individual. Let's say Jill gets into a bicycle accident. We can know what her health would be if she goes to the hospital, or we can know what her health would be if she just stayed home, but we can't know both. If we did know both, we could really easily calculate the causal effect of the hospital on Jill's health by looking at the difference in potential outcomes. If we look at the average difference in potential outcomes for all individuals, we could then calculate the average causal effect of hospitalization on health for all individuals, called the average treatment effect, or ATE for short. For any individual, we can only know one of the two potential outcomes. For people who are hospitalized, H is equal to Y and N is unknown. And for people who aren't hospitalized, N is equal to Y and H is unknown. The unobserved potential outcome for an individual is called the counterfactual. We need to know the counterfactual outcomes in order to know the true causal effect of hospitalization on health, but the counterfactual outcomes are inherently unknowable. This conundrum is called the fundamental problem of causal inference. So what are we to do? Well, let's make do with what we have and calculate the average health status of treated and untreated individuals. If we subtract the average health of the treated from the average health of the untreated, we find that hospitalized individuals scored their health a full 2 points lower than non-hospitalized individuals. If we were to interpret this causally, we would conclude that hospitalization caused health to go from good to poor, which is probably ridiculous. The issue here is a selection problem. Do hospitals make people sick, or do sick people go to hospitals? We wouldn't have to worry about this if we could observe the counterfactual outcomes, since then we could see that the sick people in hospitals would likely be even sicker had they not been hospitalized. But alas, we're thwarted by the fundamental problem of causal inference. This difference that we calculated here is called the simple difference in means, and we can write it out like this. We look at the average outcome conditional on being hospitalized and subtract the average outcome conditional on not being hospitalized. Next, we can rewrite this using our potential outcome variables. For the treated, the actual outcome is equal to the potential outcome under hospitalization, and for the non-treated, yi is equal to ni. Okay, now we'll introduce this term. Notice that since we're subtracting something from itself, it equals 0, so we can add it to our expression without changing anything. Notice that this term here is one of the unobservable counterfactual outcomes. It's the average health of the non-hospitalized in a world where they were hospitalized. Okay, our expression for the simple difference in means now looks like this. If we rearrange some terms and add some brackets for clarity, wow, isn't that amazing? Okay, it might not be obvious how it helps us, but let's take a closer look. First, look at this term. It's the difference between the observed health of hospitalized people and the potential health of those same people if they hadn't been hospitalized. In other words, this term is the real bona fide causal effect of hospitalization on health for the treated group, or the average treatment effect on the treated. This second term, then, is the difference in non-hospital outcomes between people who were hospitalized and those who weren't hospitalized. In other words, this term in blue represents selection bias. This entire expression tells us that the simple difference in means is equal to the real causal effect that we're interested in, plus selection bias. This formula can also tell us whether the bias is positive or negative. Which is likely to be greater? The average health of individuals who chose to go to the hospital if they had in fact stayed home, or the average health of individuals who just stayed home? It's very likely that people who chose not to go to the hospital did so because they were healthier in the first place. So the latter term is greater, meaning that the difference is a negative number. Why does this matter? Well, because the bias term is negative, we can be pretty sure that the simple difference in means that we calculated is an underestimate of the true causal effect of hospitalization on health. In fact, it could very well be the case that the average treatment effect on the treated is positive, meaning hospitals make you healthier, but the bias term is such a large negative number that our simple difference in means becomes negative. This is why selection bias is so dangerous. Finally, we can rewrite this so that it applies to scenarios beyond healthcare and hospitalization. Rather than the variables hi and ni, we can use y1i to represent the potential outcome under treatment, and y0i to represent the potential outcome under non-treatment. Being able to sniff out potential selection bias is one of the most important skills you can develop when doing empirical work. So let's look at a couple more examples of situations where selection bias can hide the truth. The first example comes from that bastion of economic insight, reality television. More specifically, the show Kitchen Nightmares.
What are you?
An idiot sandwich.
If you haven't heard of it, the show is about a British chef with a colorful vocabulary who visits restaurants on the brink of failure and helps them change their business to hopefully turn things around.
Hey, are we one?
Oh yes, today I'm on my own.
Yes, follow me,
In fact,
please.
most times I'm always on my own.
Insipid. Gloop. What the hell is that? Looks like it's just had a giraffe's tongue cut out and deep fat fried.
Are they popular on the menu?
People really like them.
No doubt half the customers are drunk.
I don't even think he likes the water.
If that's beef, then, hey, I was born in Bangladesh.
They've got it wrong on the menu. It's not a crab cake. It's a crap cake.
I love moussaka, but that is miles off. Moussaka. Moussak.
Seafood crepe. Yeah, that's seafood crap.
Take a bite of that cod, it's almost like you've got a breaded condom in your mouth. Oof.
Can I get you anything? No?
A sick bag.
It's like it's been left out for days and it's been attacked by cats.
Yes, chef. Yes, chef.
Okay, great. Remove your blindfolds. Beautiful.
Oh my God. Wow, this is gorgeous. It is amazing.
Gone is that depressing, tacky look of the 80s. We have completely transformed this gorgeous little room. It's a restaurant of today. It's got that fresh, contemporary feel. Wow. You okay? Look. Isn't it amazing?
It is amazing.
Just like in our hospitalization example, we have a treatment variable, participation in the show, and an outcome variable, the rate of restaurant failure. First, let's start by calculating a simple difference in means. To do this, we need the proportion of restaurants that are featured on the show that fail after 3 years, and the proportion of restaurants not featured on the show that fail after 3 years. After researching the show a little bit, we can find that 62% of restaurants featured on Kitchen Nightmares had closed their doors 3 years after their respective episode had aired. For the failure rate of non-treated restaurants, this paper found that 58% of all restaurants that open eventually shut down after 3 years. If we subtract 58% from 62%, we get a simple difference of means of 4%. A naive observer might then conclude that participation in the show makes restaurants 4% more likely to fail, the opposite of what is intended. But remember, this 4% difference is equal to the true causal effect of the show, plus this bias term here. This first part is a counterfactual. It's the fraction of restaurants featured on the show that would have failed in a world where the show didn't exist. The second part we already know. It's the failure rate of all restaurants not featured on the show, or 58%. Do you think the bias term will be positive or negative? Is the counterfactual failure rate of featured restaurants larger or smaller than 58%? Well, because the show only chooses to feature restaurants that are in distress and thus about to fail, we should expect this counterfactual failure rate to be a fair bit higher than 58%. Thus, the bias term is positive, and the simple difference in means is an overestimate of the true treatment effect. It's possible, maybe even likely, that the show actually does reduce the failure rate of restaurants, despite what the simple difference in means implies. Let's look at one more example. Before I got married in 2018, the priest required that my wife and I take a marriage prep class designed by the Catholic Church. These classes really work too, I remember him saying. The national divorce rate is around 50%, but for people who take this class, that number is around 20%. So the communication skills they teach you must be really valuable. Unfortunately, the priest was confusing the simple difference in means for the true causal effect of the classes. Let's go back to our formula and think about this bias term again. Just like last time, we know that this term is 50%, and this term is a counterfactual. It's what the divorce rate would be for the people who took the classes if they hadn't taken them. What do you think this term is? Greater or less than 50%? Well, seeing that only people wanting to get married in the Catholic Church are required to take the marriage prep classes, and the Catholic Church is notoriously anti-divorce, it's very likely that the attendees of the classes would have a lower divorce rate than the general population, even without the classes. Thus, this bias term is negative, and the simple difference in means is likely below the true causal effect of the classes. In other words, the policy probably doesn't have as big of an effect as the simple difference in means might initially suggest. We've seen multiple examples of how selection bias can muddle our results. Selection bias can make policies look more effective than they actually are, like in the marriage class example, or less effective than they actually are, like in the kitchen nightmares example. So what can we do about it? Well, in the next video, we'll take a look at the most effective tool econometricians have for eliminating selection bias: random assignment.